Dear students, good morning. On last class, you learned the statement of Newton's first law of motion and your experienced life situations showing Newton's first law of motion or law of inertia. Today class, I am going to discuss on three topics. First one, illustrations of Newton's first law of motion. Second one, inertia and mass. And third one, Newton's second law of motion. First, I am going to take account of illustrations of Newton's first law of motion. How can it demonstrate an activity to show Newton's first law of motion? Let me see the first activity. Make a pile of similar carom coins on a table and attempt a sharp horizontal hit at the bottom of the pile using another carom coin or striker as shown in figure. What can you observe? You observe that only the carom coin at the bottom of this pile is removed when a fast moving carom striker hits it. Here, if the hit is strong enough, the bottom coin moves out quickly. Once the lowest coin is removed, the inertia of the other coins makes them fall vertically on the table. On next, you see the second activity. Suppose I place a 5 rupee coin on a stiff playing card covering an empty glass tumbler standing on a table, where I have placed this coin on this playing card so that it can direct towards the bottom of the tumbler as shown in figure. Give the cardboard a sharp horizontal flick with the finger fast. What is it observed? You observe the motion of the coin. You have seen that when the card shoots away, the coin has fallen vertically into the glass tumbler. Why did it happen? Think about it. It happened due to its inertia of rest. You can understand that the coin always tries to maintain its state of rest, even when this card flows. In last class, you studied that an object, when it is in the state of rest, will have the tendency to continue its state unless compelled by an external unbalanced force to change its state. Here, the object is coin and external forces act only on this cardboard. So the coin always tries to oppose any change its state. It means that it has a tendency to continue in its state of rest. Hence, it falls down. This tendency shown by this coin is known to you. What is that? Inertia of rest. From examples and activities I introduced in earlier section, you could be known very important term, that is a tendency of a body. I means what is that? Inertia. And you studied different types of inertia and related daily life situations. Now I ask one question. If inertia has any dependence on mass, or if it has any relation with mass, now you are going to look into this subject. Are you thinking about if all bodies have same inertia? You know that it is easier to push an empty box than a box full of books. Why? Because first one has lesser mass than second one. Now you have erased one doubt. What is mass? Mass is total amount of matters contained in a body. If you kick a football, it flies away. But if you kick a stone of the same size with equal force, it hardly moves. You may in fact get an injury in your foot while doing so. So you should not practice this. Only you need imagination to understand it. From demonstrated second activity in previous part, instead of that 5 rupee coin, if I use a 1 rupee coin, what does it happen? It needs only lesser force to flick the playing card for its flight. A force that is just enough to cause a small cart to pick up a large velocity will produce a negligible change in the motion of a train. This is because in comparison to the cart, the train has a much lesser tendency to change its state of motion. It means that the train has more inertia than the cart. These situations or experiences show there is dependence of mass on inertia. Quantitatively, the inertia of an object is measured by its mass. More massive objects, that is, which are heavier, offer larger inertia. Inertia of an object is directly proportional to its mass. Heavy object has large inertia and light object has less inertia. Then it is concluded that mass of an object is a measure of its inertia. Next session you are going to study Newton's second law of motion. Newton's second law states that acceleration of an object depends on its mass and applied force on it. Its mathematical form is F is equal to ma. From given video, on soft hammer striking the system, the raised ball from it covers lesser distance, but on applying more force, it speeds up more on its next move. Look at the two swings wherein seated by two members of different weights. When it is given same push on both, if they are speed up same? No. First one covers more distance. It means more accelerated by the first one than second one. Why? Because acceleration depends on mass of an object. First person has lesser mass than second one, so first person is accelerated more than second one. In next situation, if more push is given to first person, what happens? He covers more distance than his earlier covered distance, which means that acceleration depends on force. When more force is applied, acceleration is more. Newton's second law of motion can be formally stated as follows. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. It is one form of Newton's second law of motion. In other words, how much an object accelerates depends on the mass of the object and how much force is applied to it. The equation for this is force is equal to mass into acceleration, that is F is equal to ma. Since acceleration is proportional to net force and acceleration is proportional to 1 by mass, or A is proportional to F and A is proportional to 1 by m, then A is equal to F by m. Forces acted on objects are unbalanced, which can produce only acceleration in them. The slide is helpful to memorize you always. The dependence of acceleration produced in a body on net force acted on it and body's mass. Next I am going to talk over second form of Newton's second law of motion. Before you are introduced it, first you want to know about a new concept, that is momentum. Let you recall some observations from your everyday life situations. During the game of table tennis, if the ball hits a player, it does not hurt him. But when a fast moving cricket ball hits a spectator, it may hurt him. A truck at a rest does not require any attention when parked along a roadside. But a moving truck, even at speeds as low as 5 meters per second, may kill a person standing in its path. A bullet of small mass may kill a person when fired from a gun. This observation suggests that the impact produced by the objects depend on their mass and velocity. Similarly, if an object is to be accelerated, we know that a greater force is required to give a greater velocity. In other words, this appears to exist some quantity of importance that combines the object's mass and its velocity. This quantity is momentum. This impact produced by the objects depends on both their mass and velocity. Momentum was first introduced by Newton, which combines the object's mass and its velocity. Momentum is defined as the product of mass and velocity of an object. Mathematically, it can be written as P is equal to mv. Momentum has both direction and magnitude. Its direction is same as of velocity. Its SI unit is kilogram meter per second. Next, you are going to see another situation in which a car with a dead battery is to be pushed along a straight road to give it a speed of 1 meter per second, which is sufficient to start its engine. If one or two persons give a sudden push, that is unbalanced force to it, it hardly starts. But a continuous push over some time results in a gradual acceleration of the car to this speed. It means that the change of momentum of the car is not only determined by the magnitude of the force but also by the time during which the force is exerted. It may then also be concluded that the force necessary to change the momentum of an object depends on the time rate at which the momentum is changed. Here, Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the external force applied on the body. This change always takes place in the direction of the applied force. This rate of change of momentum can be obtained by dividing the change of momentum by the time taken for that change. The consequence of Newton's second law of motion is F is equal to ma. Next, you are going to study how can we derive Newton's second law of motion mathematically. Consider an object of mass m is moving along a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F throughout the time t. You know that it needs an unbalanced external force to change the state of body. Here body is uniformly accelerated, then force applied is the constant force. The initial and final momenta of the object will be P1 is equal to mu and P2 is equal to mv respectively, where u and v be the initial and final velocity of the body respectively. Then the change in momentum is equal to P2 minus P1, that will be equal to mv minus mu, which is equal to m into v minus u, as m is common. You already studied that momentum is the product of mass and velocity. Then rate of change in momentum is equal to m into v minus u upon t. According to Newton's second law of motion, we have F is proportional to m into v minus u upon t. So F is equal to km v minus u upon t. Then F is equal to kma, where a is equal to v minus u upon t. A be the acceleration, it is the rate of change of velocity, and k be a constant of proportionality or proportionality constant. Putting the values of m as 1 kilogram, a as 1 meter per second square, then F becomes as 1 Newton. So 1 Newton is equal to K into 1 kilogram into 1 meter per second square. Then K is equal to 1. It is the unity. When we have considered K is equal to 1 unit, then above expression becomes as F is equal to 1 into ma is equal to ma. This represents the second law of motion, and it also defines 1 Newton of force. How can we define 1 Newton of force? Is the amount of force applied on an object of unit mass, that is 1 kilogram, to accelerate about 1 meter per second square in its directions, or the direction of force. SI unit of force is kilogram meter per second square or Newton. It is represented by capital letter N. The second law of motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. Dear students, today homework questions are given in this slide. Okay, thank you. Have a nice day.